Hello everybody. In this video, we're going to look at finding integrals or calculating integrals for more complicated functions. Now that we know that integrals are directly related to antiderivatives, we can really calculate the integrals for any function that we know how to find the antiderivative of. But at this point, the only functions that we really know how to take the antiderivatives of are polynomials, or very simple functions, simple exponential functions, or simple power functions. But that's about it. What we're going to look at today is, well, how do we expand that? How can we find antiderivatives for more complex functions? And today we're specifically going to look at what do we do if we have a function inside of another function? What do we call that again, right? We call that composite functions. How do I calculate the integral of something like this? Well, it turns out we're going to use a process called integration by substitution. But in order for us to be able to understand this process, first of all, I need to kind of remind you guys about a couple of things. First off, let's remember that this dx is part of the notation, and it also tells me what variable I'm integrating in terms of. This is important to know in case there's multiple variables in your function, which we're going to see in just a little bit. The other thing I wanted to remind you of is, remember, we have a derivative rule for composite functions like this. What's my derivative rule? It's the chain rule, where I will take the derivative of the outside function, keep the inside function the same, and then multiply by the derivative of the inside function. So now that we remember those two things, let's go back to this initial question. How do I find the integral of a composition of functions, a function inside of a function? Well, mathematicians have spent a long time trying to figure this out. And it turns out there's no way to directly do this. There's no way to directly integrate a composition of functions. Instead, what we have to do is we have to go back to this chain rule and recognize that, okay, well, the closest I can get is reversing the chain rule. If I can reverse the chain rule, right, if I can go this way, that counts as an antiderivative. But in order for me to do that, that means that my function has to start in this form. And this is where the substitution comes in. So let's consider a function that's already in this form. What do I mean by that? What I mean by that is, let's consider an integral where I have a function inside of a function, but I have the derivative of the inside function being multiplied on the outside of this function. And that's what I wanted to take the antiderivative. Do we see how that kind of matches the result of the chain rule? It's not exactly the same. What's missing is the fact that it doesn't have to be the derivative of my f function, because if f is simple enough, I can find an antiderivative of that outside function. The important thing is that I have the derivative of the inside function being multiplied on the outside like that. So let's assume we have a function in this form. I can use substitution to simplify this a little bit. Let's make a substitution here where we let u equal that inside function. This integration method is also called u substitution sometimes, because we like to use that variable u when we do this substitution. Well, if I just do this substitution right now, I'm going to get f of, now instead of g of x plugged in, I just have this variable u representing your function g of x. But I can't quite put that there for g prime of x. So I still have this times g prime of x dx. Now remember, dx represents me integrating in terms of x. But now I have this function that's in terms of both u and x. How do I deal with that? Well, the answer is to just focus on this piece and say, well, since that's a derivative, let's take the derivative of u over here. If I take the derivative of u, I get du over dx is equal to g prime of x. Pretty simple, right? Two different notations for a derivative, one with my Leibniz notation and the other just my function notation. So if I take the derivative of u, I get g prime of x. But notice what happens if I let's move the dx over to the other side. We've seen this before. We saw this in 1.7 when we talked about differentials. So I get g prime of x dx. So take a look at that. by just using a little bit of notation manipulation, I can see that I can rewrite g prime of x dx. I can rewrite that as du as long as u is equal to g of x. So those two things are interchangeable, meaning I can come back here and say, oh, well now this is just the integral of the function with u plugged in multiplied by du. And now what do we notice? Now this is telling me I'm integrating in terms of u instead of integrating in terms of x. And therefore, to find this antiderivative, it's as simple as finding the antiderivative of f. I get capital F with that function still, or with that variable still plugged in. Right? Just like how I would do it if it were x instead of u. It would just be the antiderivative of f with x plugged in. What does that mean? But that means, remember, u is equal to that inside function g of x, and so then I would need to plug that back in when I'm done. Don't forget your plus c, because this first example is just an indefinite integral. And that's how the chain rule works, is if I have a function in this specific form, it has to be in this specific form. Why? Because it allows me to undo the chain rule in order to come up with an antiderivative. But what's nice is I have a procedural way of doing this using this idea of substitution. So let me show you a quick example of how this actually works with a real function. Consider this. Let's say I have e to the x squared times 2x dx. This qualifies as being in this form. Why? Because first of all, I have a composition of functions. I have a function inside of another function. My x squared function is inside of this natural exponential function. But what else do we notice? What's being multiplied by that composition of functions? Being multiplied by it is 2x, which just so happens to be the derivative of x squared. So it falls under this form, which means I can use substitution to actually evaluate this. I can substitute u for x squared for that inside function. What would that give me? That would give me e to the u times 2x dx. Now I can't stop here because I now have an integral that's in terms of two different variables, u and x, and I can't do anything with this. I also have to get this in terms of u. How do I get dx in terms of du? It boils down to the derivative. That's what I did up here. I took the derivative of my substitution. So du over dx is equal to 2x. Multiply by dx to get that differential notation. What do I notice? 2x dx is equal to du. Here I have 2x dx, so I can replace this with du. If you want to do it a little bit more mathematically, I can solve for dx by dividing by 2x on either side, and that gives me dx is equal to du over 2x, and then I can plug this in for dx. But notice what should happen. I'm going to have 2x times this du over 2x. The 2x's cancel out. And I'm left with this integral of e to the u du. And notice how much simpler that integral is. Do I know what the antiderivative of e to the u is, or e to the x is? Absolutely. My antiderivative is just e to the u again. The antiderivative of e to the x is just e to the x. So the same thing is true for e to the u as long as this matches the variable. Since that's du, since that's in terms of u, I can take the antiderivative like normal. I'll go ahead and put a plus c. But what is u? Now I can plug x squared back in for u, and there's my antiderivative. And that's how this actually works in practice. Now that we've seen that, though, I want to contrast that with, well, what if that 2x isn't there? What if I try and take the antiderivative of just e to the x squared, and I don't include that 2x? What happens? I can still do this substitution and say, okay, let's let u equal x squared. Okay, I get e to the u dx. Once again, I can't do anything with this. I can't stop here because I can't integrate when I've got two different variables in play. I have to get the dx in terms of du. So I'll come back up here and I'll take the derivative. As you get more comfortable with this, you can start just automatically moving the dx over to the other side, like so. Du is equal to 2x dx. So now that I've got this in terms of dx and du, I can now switch this dx in terms of du by solving for dx. And I get dx is equal to du over 2x. Makes sense, the same thing we got over here. But notice what happens when I plug this in. Dx is equal to du over 2x. If I move things around a little bit, I get edu over 2x times du. So now I'm integrating in terms of u, but what's my problem? I still have an x in the integral, meaning I still can't solve this. It's still in terms of two different variables. So without that 2x being there, I can't actually eliminate my x variable. And if I can't eliminate the x variable, I can't integrate in terms of u. So once again, that's why in order to be able to use integration by substitution, we need it in this specific format. Now, I do have to be careful when I say that, because it turns out it doesn't have to be in exactly that format. I'm going to change this one more time. What if I have the definite integral of e to the x squared times x dx? What's different? This time I'm not including the 2. Let's say I just have the x there. Well, once again, my inside function is x squared, so I still want to make that same substitution. And once again, in order to deal with this dx, I'm going to need to take the derivative of my substitution of my inside function. So I get du is equal to 2x dx. I want to replace dx with du, so I'm going to solve for dx. And I get that same value of du over 2x. But notice what happens now when I plug this in. I get x squared is equal to u, so e to the u times x times what's dx? Dx is du over 2x. Well now, because I have an x in the numerator and an x in the denominator, the x's actually cancel. But what doesn't cancel? The 2 doesn't cancel. So if I were to rewrite this, I'd be left with this antiderivative of e to the u over 2 du. That's not as simple as this antiderivative. But the question is, can I still find that antiderivative? Absolutely, because the only thing that's new is this extra constant here. Remember, I could rewrite this as the antiderivative of 1/2 e to the u du. Right? If I divide by 2, that's the same thing as multiplying by 1/2. And as soon as I write it like that, well, this is just a constant multiple. Meaning, can I pull it outside my integral? Absolutely. I can rewrite this as 1/2 times the integral of e to the u du. So that leaves me 1/2 e to the x squared plus c. That's, of course, after I find the antiderivative and plug x squared back in for u. So it turns out that it doesn't have to be in exactly this form, but it does have to be in roughly this form, that there's some constant multiple of the derivative that's being multiplied on the outside. So you're going to see lots of examples on the homework of different ways this is possible. And we'll look at some of those in our examples video. But the last thing we need to talk about is, how does this property work if you have bounds? So let's say I have this format where I've got a function inside of a function, and I've got maybe not exactly the derivative of the inside function, but maybe just some constant multiple of the derivative of the inside function. Like we just saw, I can still use integration by substitution in this case. This is still okay. But what do we do if I have bounds? Well, the first thing to recognize before we get started on this is, what are these bounds in terms of? These bounds are in terms of whatever variable that's in terms of, because that's what we're integrating in terms of. So these bounds are in terms of x. They represent x values. I'm integrating in between a and b along the x-axis. Well, as soon as I do my substitution and say, okay, I want to let u equal g of x, I'll take my derivative of both sides and I get du is equal to g prime of x dx, right? Turn it into the differential. Well, what does that allow me to do? That allows me to rewrite g of x as just u and replace this g prime of x dx with du. I now have an integral that's completely in terms of a new variable, u. If I keep the bounds as going from a to b, this is now a fundamentally incorrect integral. Now, it may not seem incorrect because it looks normal. You can go solve this and plug in your bounds. But this is fundamentally incorrect, and the reason why is because these are still x values. But my integral is in terms of u. So what do? How do I fix this? Well, all I need to do to fix this is convert these bounds in terms of u. Get them in terms of u. And how do I do that? You can do that just by plugging them in to your inside function. So your lower bound will just be the value you get when you plug in a to your inside function. Your upper bound is just going to be the value that you get when you plug in b to your lower function. So the correct way to write this would instead be g of a to g of b, because both of those will represent u values now that my antiderivative is in terms of u. And the nice thing about substituting is once I'm finished with this, right, I find the antiderivative in terms of u. I'm going to have this constant being multiplied on the outside, right, because I can bring that constant out in front if I'd like. But since this is a definite integral, instead of having a plus c, I'm going to have these bounds. So I need to evaluate this from g of a to g of b. Now we might think, okay, well now we got to plug g of x back in. But because we've shifted my bounds, I can just evaluate this from here. I don't have to plug my equation back in because I've already put in the work to switching the bounds. So now that these bounds are in terms of u, I can plug those in directly into my antiderivative and finish. We'll see an example of this in the examples video as well. But that sums up this method called integration by substitution, which I can use as long as my function is set in a specific way. Now, when you're working through the homework, something to keep in mind is you don't have to check necessarily whether the function's set up in the right way. You can just go ahead and start integrating by substitution, and if you can't eliminate that x, that means you can't actually solve it using integration by substitution. Go ahead and get started on the homework, and if you have questions, go ahead and take a look at the examples video. Thanks.